In this video, we're going to learn about the applications of electrolytic cells, as well as how to do cell stoichiometry questions. So there's a variety of different uses for electrolytic cells. One of them being electrorefining, which is where you take an impure metal, you put it at the anode, and then you use electrolysis to purify it. Okay, so in electrorefining, with your anode, remember anox gets thin while red cat gets fat. So with your impure metal being your anode, electrolysis is going to cause it to break down essentially, and then through this reaction, the pure metal will be deposited at the cathode because red cat gets fat. The cathode is going to increase in mass while your anode is decreasing in mass. Another use of electrolytic cells would be electroplating, which would be what this diagram is trying to represent here. Okay, so essentially what you're doing with electroplating is you're essentially depositing a very thin layer of some pure metal onto some substance. Okay, so with this, and that substance is going to be a metal, I should specify that. So electroplating So what that is you're depositing a thin layer of one metal onto a piece of another metal. Okay, so in this diagram here, here is our cathode, and this is where pure copper is going to be deposited. So your anode is going to decrease in mass, so it's going to be broken down through this process, and those pure copper ions are going to get reduced and deposited on the cathode there. And then last but not least, electrolysis is just the general name for the reaction that is being completed in these non-spontaneous reactions where we have to use a power source in order to force the reaction to go. And if we're not depositing like a thin layer of a pure metal onto something else, then we can use electrolysis to produce gases. So examples of gases that we would want to produce would be something like chlorine, oxygen gas, or hydrogen gas. So oxygen, that's useful for use on something like a space shuttle, just so that you can have an environment that people can live in. Okay. And then we would want to use hydrogen gas for fuel cells. So fuel cells are used to cleanly produce electricity, and it can be used in situations like electric vehicles. So fuel cells are used to help power electric vehicles there. And lastly, why we would want to use chlorine gas is because it's a good disinfectant for water treatment. So we'd be using it to treat things like swimming pools or sewage. All right, moving on to cell stoichiometry. So effectively, it's just like any other form of stoichiometry that we've worked with, either in Chem 20 or earlier in Chem 30. The only difference is going to be how we get the equation that we use in order to figure out what our mole ratio is. So a cell stoichiometry question is usually concerned only with the reaction either at the cathode or the anode of an electrochemical cell. So that means you're only going to have to write a half reaction. So since electrons are included in half reaction equations, you're going to need to learn how to calculate the moles of electrons. The total number of moles of electrons passing through an electrochemical cell really depends on the current and time. So the current that's passing through the electrochemical cell and just for how long that current is applied to that electrochemical cell. So to find the moles of electrons, we're going to use the formula below. So right here. So Ne is the moles of electrons. I over here, that's going to be current. T is for time, which is usually in seconds. Current could be in coulombs per second or in amps. So the symbol for amps is just A. And 1 coulomb per second is just equal to 1 amp. Okay, and then it's divided by Faraday's constant, which is 9.65 times 10 to the power of 4 coulombs per mole of electrons. So that constant there, you can find it in your data booklet. If you go to page 3, you'll find it kind of midway through right here. So you don't have to memorize this number. You have it given to you in your data booklet. Okay, but just know that this formula is not given to you in the data booklet. All right, so for our first example, how many moles of electrons pass through the anode of a cell in 10 minutes when the current is 6 amps? All right, so because it's asking how many moles of electrons, that's what we're trying to figure out. So moles of electrons, we have no clue. Okay, but for the time, that's 10 minutes, but remember, time needs to be in seconds. So we gotta work on converting time from minutes to seconds. So 10 minutes, I'm gonna use unit analysis to do this. So since minutes is in the top, How I'm going to cancel it out is by putting minutes in the bottom and then putting seconds in the only other spot available. So we always start with the bigger of the two units. In 1 minute, there's 60 seconds. So 10 times 60, that's going to give us 600 seconds. Okay, and then last but not least, our current is 6 amps. Oh, I should be writing I for current, not C. Okay, so now that we have our list of givens, let's start off with our formula here and plug in our numbers. So current, that was 6 amps, which I'm going to write as coulombs per second because they're equivalent, just so you can see how the units cancel out. Time, that's 600 seconds, divided by Faraday's constant, so that's that 9.65, times 10 to the power of 4, and the units are coulombs per mole of electrons. Okay, so coulombs is on the top and the bottom, so they cancel out. Same with seconds, and what we're left with is moles of electrons here. So let's put this into our calculator. So 6 times 600 divided by 9.65, and then I'm going to go second function log to get that 10 to the power of 4, hit the right arrow to get out of the exponent, close the bracket, and then hit enter. So we get 0.0373, goes on forever. Okay, and so our units are moles of electrons. Now, for every calculation, we got to take care of sig digs. So this number has 3 sig digs, same as this number. So our answer needs to be put in 3 sig digs. So counting from the far left, remember, leading zeros don't count as sig digs, but the 3, 7, and the 3 does. Okay, so actually what I'm going to do, I just need one more digit. So it looks like there's a 0 behind the last 3. Okay, so I'm just putting an extra digit just to show you like what's happening with the rounding. So our cutoff line is right here. So my final answer will be 0.0373 moles of electrons. All right. So for these types of questions, in order to identify them, what you're looking for is words like plated, current, or time. That is your clue that this is going to be a cell stoich question if you see one of these words here in the question. So for our next example, it's asking us what mass of zirconium could be plated. So this tells us it's a cell stoich question onto the cathode using a current of 12 amps applied for 2 hours. Okay, so I also want to focus in on the fact that we're dealing with the cathode here. So it's going to be a reduction reaction because red cat gets fat. Reduction happens at the cathode. So what we're going to do is we're going to start with a half reaction, and just note that current and time, they always belong to the electrons. Time must always be in seconds, and then you're just following the steps of stoichiometry. Okay, so as a quick reminder of the 4 steps to solve stoich problems, let's write them out. So step 1, you're going to want to write a balanced chemical equation. So I'm going to abbreviate equation to EQT. Step 2, you need to find the moles of your given substance. So that's meaning whatever you have the most information given for, that's your given substance. So find the number of moles of your given substance. Step 3, you're going to use your molar ratio to convert the moles of your given substance to the moles of your wanted substance. So mole ratio. And just know that electrons absolutely can be put in your mole ratio. And just as a reminder, the mole ratio is the coefficient of what you want divided by the coefficient of the substance that you're given. And then step 4 is essentially answer the question. So you're going to be converting the moles of your wanted substance into whatever units the question is asking for. Okay, so let's start here. So we're asked what mass of zirconium could be plated. So we know that zirconium solid, since it's being plated onto the cathode, that's going to be one of our products. Okay, so because the solid metal is one of our products, that's telling me that the aqueous ion of zirconium needs to be one of our reactants here. So I need to figure out what is the charge that zirconium likes to have here. Okay, so there's zirconium. It's right here, number 40, and it likes to have a charge of 4+. So let's use that to do step 1, writing our balanced chemical equation. This will just be a half reaction that happens at the cathode. Okay, so zirconium, it starts out as an ion. Okay, and it gets plated. So it goes from an ion to a solid. And now what we need to do to balance this half reaction is, like, first off, we need to balance out anything that isn't, if we're going through all our steps, anything that isn't hydrogen or oxygen. So we need to balance zirconium. So there's one zirconium on each side. It's already balanced. There's no hydrogen or oxygens to worry about balancing. So now I'm going to move towards balancing the charge. Now the overall charge on the reactant side is 4+, right? Whereas on the product side is 0. So I'm always going to go to the more positive side and add my electrons there. Okay, and I'm looking to make both sides have the same overall charge. So I'm going to add 4 electrons, right? So since electrons have a negative charge, we're going to minus 4. So now the reactant's overall charge is 0, which matches up with the product side. So that's balanced. Okay, now what I'm going to do is I'm just going to organize my information here. So we're given current, which belongs to the electrons, of 12 amps. Okay, and it's applied for 2 hours, so that's time, which time should be in seconds, so we need to convert this. So 2 hours, and you can either use 2 conversion factors, so these things are what I call conversion factors, or you could do it in 1. I'm just going to show you how you would do it using 2 as well as 1. So with hours, we want to cancel that out. Okay, we want to get to seconds, but not everybody knows how many seconds are in an hour. So I'm just going to break it down from converting from hours to minutes and then minutes into seconds. So hours to minutes, we're starting off with the bigger of the two units, 1 hour, or in 1 hour there's 60 minutes. So that eliminates the hour unit. Okay, and now we need to cancel out minutes to get to seconds. So since minutes is in the top, I'm going to cancel it out by putting minutes in the bottom and then put seconds on top. So in 1 minute, there's 60 seconds. So what this means is we're going to take all of our numerators, multiply them together, multiply all of our denominators together, and then we can divide the two. Okay, so 2 times 60 times 60 is going to be 7,200. Okay, now the denominators, they just multiply to 1, and any number divided by 1 is going to stay the same. So this is going to be 7,200 seconds. So if you wanted to convert from hours to seconds just in one step, what you would do is you would take those 2 hours, and then we want to cancel out hours, so it's in the top. I'm going to put hours in the bottom, then put seconds on top. And in 1 hour, there's going to be 3,600 seconds. Okay, so that's coming from the 60 times 60 here. So if you want to do this in one step, you have to know that there's 3,600 seconds in an hour. And to prove you'll get the same answer, let's do this. So 2 times 3,600 and then divided by 1 isn't going to change anything. You still get 7,200. Okay, so you've got some options there. If you want to do it this way, that's fine. If you want to do it this way, also fine. You just need to remember how many seconds are in an hour. Okay, what else do we need to worry about? So we're asked what mass of zirconium. So anytime you're asked for a mass or you're given a mass, usually you're going to want to figure out what is the molar mass of that. So zirconium, it's not a special element, it's not diatomic, it's not polyatomic, so we just want to find the molar mass of one atom of zirconium. So our molar mass for zirconium is 91.22, so that's our molar mass. And the units are grams per mole. Okay, so now that we have our information organized, we can move on to step 2, which is find the number of moles of the given substance. So for that, we have the most information given for the electrons, so that's where I'm going to start. So find the number of moles of electrons using moles of electrons is equal to current multiplied by time divided by Faraday's constant. So our current is 12 coulombs per second, which is the same thing as amps, times by time, so 7,200 seconds, divided by Faraday's constant, that's that 9.65 times 10 to the power of 4 coulombs per mole of electrons. So coulombs and seconds are going to cancel out. We're left with moles of electrons. So I'm going to take 12 times it by 7,200 and then divide by 9.65 and then second function log to get that 10 to the power of 4, hit the right arrow to get out of the exponent, close the bracket, hit enter, and we get 0.8953, goes on forever. So that's our moles of electrons. Okay, so that's step 2 done. And now we need to do step 3, which is mole ratio. So coefficient of what we want divided by coefficient of what we are given here. So times by fraction sign. So we're given electrons. All right, so that's coming from here. And we want, since it's asking us for the mass of zirconium, we are going to want this. Okay, so zirconium, that has a coefficient of 1, and then the electrons have a coefficient of 4. So we're taking this number and we're making sure to use the entire raw number that we got in our calculator, and then we're going to times it by a quarter, or you could also say just divide it by 4. Both will get you the same answer. So I'm going to divide by 4. Okay, so our answer is 0.2238. Goes on forever. And that's going to be moles of zirconium. Okay, because with the electrons, if you treat it kind of like units, they cancel out because you got 1 in the top, 1 in the bottom. Okay, so step number 4, answer the question. So we need to convert from moles of zirconium into grams of zirconium. Okay, so how we're going to do that, I'm going to show you the unit analysis way of doing that, but if you really don't like unit analysis, what you could do is you could go mass is equal to moles times molar mass if you really want a formula. Okay, but what I'm going to do, I'm going to start off, so this is how you would do it with unit analysis. So 0.2238 goes on forever, moles of zirconium. So we know we want to cancel out moles and we want to get to grams. So I'm going to go times by fraction side. Moles is in the top, so I'm going to put moles in the bottom. And I want to be left with grams, so I put that on top. So grams per mole, what has the unit of that? Molar mass. And look, we already have it because we organized our information. So 91.22 grams per 1 mole. So this number is going to go wherever the grams goes. So I'm going to put that in the numerator. Okay, and if it really bothers you to not have a number in the denominator, you would put a 1 there. So what we're going to do is we're going to take our moles of zirconium and multiply it by our molar mass of zirconium, which is exactly what we do here. Okay, now what's the advantage to unit analysis versus just using a formula, since they both give you the same answer regardless? With unit analysis, you don't have to memorize formulas, because keep in mind, with Chem 30, none of your formulas are given to you. So do you want to spend the brain power on memorizing formulas or using unit analysis? It's up to you. You need to make that decision. Okay, so let's times this by 91.22. And we get 20.4181, goes on forever. So that's grams, and then looking at my given numbers, this is in 4 sig digs, whereas this is in 3 sig digs, so you always go with a number with the least amount of sig digs, so our answer needs to be in 3 sig digs. So that's how we're getting 20.4 grams of zirconium plated. Okay, example 3. How long does it take to plate 0.198 grams of copper from copper 2 ions using a current of 5 amps? At which electrode would you put the object that you want to plate? Okay, so since we're plating something, that means we are increasing the mass of something, because plating just means that you're depositing a thin layer of one metal onto another metal. Okay, so that's going to result in an increase in mass. What do we know is related to an increase in mass? Red cat gets fat. Reduction happens at the cathode, and the cathode increases in mass. So we need to be using a reduction reaction, and for which electrode would we put the object at? We would put it at the cathode. So I'm actually going to start by answering the last question first. So really this question is just asking us which electrode will increase in mass. So for our mnemonic device, red cat gets fat. So we choose the cathode because that's where the solid metal is going to be deposited due to the reduction reaction. And again, red cat gets fat means reduction happens at the cathode, which increases in mass. So cathode, because that is where the solid metal gets deposited. All right. So let's get to the other question. How long? So we're looking for time here. Now the question doesn't specify what units it wants time to be in. So if the question doesn't specify what units it wants for time, assume seconds. However, if the question says that it wants your units for time to be in hours or minutes, then obviously follow what the question's saying. Okay, so the question doesn't state what it wants for units. Seconds is fine. But if the question asks for minutes or hours, then you have to convert from seconds to whatever the question's asking for. Okay, so we're still going to follow the same 4 Stoich steps. So step 1, we need to start out with our balanced chemical equation. We know that we are plating solid copper from copper 2+ ions. So let's start there. So plating copper means that copper solid is our product. Okay, and it says we're doing it from copper 2 ions, so that's telling you your reactant is those copper 2 plus ions. So remember, ions are always aqueous. So copper on the reactant and product side, they're both the same, so that's balanced. We don't need to worry about balancing oxygen or hydrogen, so now we need to move on to balancing the overall charge. So on the reactant side, we have a charge of +2, whereas on the product side, we have a charge of 0. So I'm going to go to the more positive side and add my electrons there. So those 2 electrons, because electrons have a negative charge, okay, that's going to subtract 2. So my reactants now have an overall charge of 0, same as the products, so that is balanced. All right, so now that we have our balanced half reaction, and it is reduction because the electrons are being gained, we know that because they're on the reactant side. And so now I'm just going to organize my information. So how long does it take? We're looking for time. Time goes with electrons, so I'm going to organize it here. And we're told that we plate, so that's a mass, and it goes with copper solid of 0.198 grams. And whenever we have mass, we're going to want to figure out molar mass of that. So I'll do that in a second. I just want to get the 5 amps done first. So that's current. So amps or coulombs per second, they are equivalent units. So 5 amps, or we could say 5 coulombs per second. Now let's move on to the molar mass for copper. So let's find where copper is. So copper is going to be having a molar mass of 63.55. So 63.55 grams per mole. There we go. Okay. So step 1, write a balanced chemical equation. Done. Now we need to do step 2, find the number of moles of the given substance. Okay, so what were we given the most information for? Well, that would be copper. So I'm going to continue this up here. Okay, so we know we want to find moles. If you really want a formula to use, you can take that mass is equal to moles times molar mass and rearrange it to isolate for moles. So molar mass is multiplying moles, so I do the opposite, which is dividing. So mass divided by molar mass is equal to moles. So actually I'm going to write that over here so that I can show you that with unit analysis we're doing the exact same thing. Okay, you get to choose whether you want to do unit analysis or use a formula. Okay, so for unit analysis, I'm going to start out with the number that doesn't have a fraction in the units. Okay, so I'm going to start out with the grams. So 0.198 grams. We know we want to cancel out grams and get to moles. How we know that is because step 2 says find the moles of the given substance. Okay, so I'm going to do my given number times by a fraction sign. So I want to cancel out grams. Grams is in the top, so I put it in the bottom. And then I put moles on top. So this is just molar mass here. So my molar mass was 63.55. That's going to go where the grams goes. Okay, so what this is saying is take this number, multiply it by 1, and then divide by 63.55, which is the same thing that you're doing in the formula. You are just taking this number, dividing it by 63.55. I'm not going to bother to go times by 1 and then divide by 63.55 because multiplying a number by 1 isn't going to change it. Okay, so we get 0.00311 goes on forever. So that's moles of copper solid. Okay, so I'm going to take that number and we're going to move on to step 3. Okay, so step 3 is use your mole ratio to convert what you're given into what you want. Okay, so keep in mind I'm still using the whole number in my subsequent calculation. So we're going times by fraction sign. So the coefficient of what we want. Since we want time, that means we're going to want our moles of electrons. So we got moles of electrons and we're given copper. So looking at our balanced chemical equation, we have a coefficient of 2 in front of electrons and 1 in front of copper solid. Okay, so if you treat the identity of the substance like a unit, copper cancels out. So what we get here, so I'm taking this number, multiplying it by 2, and we get 0.00623 goes on forever. And that's going to be our moles of electrons because those are the units that did not cancel out. Okay, so now what we got to do is step 4, answer the question. So we need to figure out time. And the formula that we can use to figure that out would be this formula here. Okay, but we're going to have to rearrange it. So I'm taking my moles of electrons is equal to current multiplied by time divided by Faraday's constant. So we want to isolate for time. Okay, so what I'm going to do is I'm just arbitrarily going to get rid of Faraday's constant first. I'm going to move it over to the left-hand side. So I'm asking myself, okay, what is Faraday's constant doing to time? Well, it's dividing, so I need to do the opposite, which is multiplying. Okay, so that cancels out. Okay, so now we're still working on isolating for time, and we're asking ourselves, okay, what is current doing to time? It's multiplying, so I got to do the opposite, which is dividing. Alright, so this is going to be the equation that I need to use in order to figure out time. So I'm going to have to move this up here. Okay, so I'm going to plug in my numbers for this. So Faraday's constant, 9.65 times 10 to the power of 4, and that's going to be coulombs per mole of electron, times by our moles of electrons, so 0.00623 goes on, moles of electrons, divided by current, which current was 5 amps, which is the same thing as saying 5 coulombs per second. Okay, so coulombs cancels out, moles of electrons cancels out, we are going to be left with seconds. So time is equal to, so how I'm putting this into my calculator, I'm going 9.65 times 10 to the power of 4. Okay, multiplied by, I'm going to go second function, and then the little negative sign to get my answer. Hit enter and then divide by 5. So there's 120.264. Goes on forever. So this is in seconds right now. So the answer says 120 seconds or 2 minutes. Like either is fair. Okay. The only thing we have left to do is just take care of sig digs. So there's 3 sig digs there, 3 sig digs there. So that's why our answer is in 3 sig digs. So 120 seconds.